So thanks for inviting me. Uh, I know this is a sort of a hyperboloidally focused seminar or webinar series. So I'll be talking a little bit about hyperboloidal methods and their applications to studying black hole ringdown in particular. And I guess I should say I'm a postdoc at the University of Illinois. So let's first start with why study black hole ringdown? Like, why is this interesting? Sorry. So let's review the basics of binary and spiral. We have two black holes represented by these two yellow spheres. They're in spiraling, emitting gravitational waves. That's what the signal down here. This is the gravitational wave strain in red. Then as they lose energy through gravitational waves, they in-spiral and eventually they merge, form this large signal. And what they form is this remnant black hole with mass m and spin a, but it's very deformed at first, and it has to relax to occur in state. As it's relaxing to that end state, it's emitting gravitational waves. And the signal looks like this. If you do a numerical relativity simulation, the signal looks like this. It turns out, it's very common, we take this signal, the ring down, we model it with what's called quasinormal modes, which are just damped sinusoids. And you obtain these frequencies, the damping times in the real part, from black hole perturbation theory. So what black hole perturbation theory tells you, and we'll review that a bit more later, is that these damping times and frequencies are related to the black hole's mass and spin. So there are two numbers here. For every mode, you can think of there are two numbers, and they depend on two numbers. So if you measure one mode, you can imagine recovering the mass and spin from just measuring one ring down mode. If you measure two ring down modes, you get a consistency test of general relativity. Do you get the same mass and spin? Is it consistent with those two ring down modes? And this all goes under the title of the black hole spectroscopy program, which is you take this ring down signal and you want to reconstruct the mass and spin from these measured quasinormal modes. And then if you measure multiple modes, you can do these consistency tests. And this was proposed in various guises long ago. And finally, with data, people are actually beginning to do this with real gravitational wave data. So what's the problem with this picture, or what's the controversy? And there are two different ways of thinking of what different problems could be. One is through data analysis and one through modeling. So let's run through data analysis first. So first, there are many quasinormal modes. In fact, there's an infinite family of QNMs. So which ones are you going to fit to data? You can't just fit all the QNMs. That's too big a parameter space. So which ones do you pick? Also, when does the ring down start? When do you begin your analysis? Is it at the peak of the strain? Is it a bit later? You can also ask how well does quasinormal modes, this picture, describe the ring down. These modes are obtained from linear perturbation theory. So you could imagine perhaps the nonlinearities inherent in the Einstein equations will also affect this picture, and perhaps these nonlinearities could be important. There could be corrections to the QNM picture. Also, even within the linearized treatment of the Einstein equations, there are non-mode solutions. So are those non-mode solutions, could those also be in your signal that you should be fitting for? So these are some questions people have. And that way, the rest of this talk will be looking at how hyperboloidal methods can help us. They're a very powerful set of tools that we can use to at least study these questions. So first, I'll just review black hole perturbation theory in more detail. I'll talk about boundary conditions and the very important role they play in determining the quasinormal mode solutions. I'll talk about how hyperboloidal slicings can help us understand these boundary conditions in a very convenient way. And then I'll talk about some applications of these methods, both in open source codes, some of which are on my GitHub, and many people have helped write these codes, and some numerical experiments with these codes to get at some of these questions. So that's the outline. But first, let's talk about modeling black hole ring down. So the final end state is a curved black hole, and you can describe it as either a deformed black hole that's relaxing to occur, or you could describe it as just a curved black hole with gravitational waves around it, and they're going to be dispersing and falling into the black hole and emitting away to infinity. Here's the curved black hole solution, just to remind you, it's in Boyer-Lindquist coordinates. A is, again, the spin, M is the mass. And to describe what the gravitational waves around the space-time, we're going to do perturbation theory. You take your background, which is Kerr, and then you expand in some small dimensionless parameter epsilon, order by order in perturbation theory. We're only going to go to linear perturbation theory, so we're just going to take this G1, the first order term, and then you could since it's vacuum Einstein equation, this is a black hole, we can just say r mu nu equals 0, simpler, and perturb r mu nu about the background. And again, we're only going to go to linear order. You could go to higher orders, but I won't be talking about that in this talk. Just linear perturbation theory for today. And the mode solutions, these Q and M's are the mode solutions to the linearized Einstein equations. You take your linearized metric and you decompose it in terms of modes. The background is is invariant under time shift, so you can always do this mode decomposition. It's very convenient. Of course, in the literature, for those who know, it's much more common to study the a scalar wave equation instead. It's called the Tucholsky equation. It's for this complex scalar psi4. Just to show you what it looks like in Boyer-Lindquist coordinates, it's a wave-like equation. So we got ourselves with 2 time derivatives here. We have 2 space derivatives. This is like an angular derivative. It's like the spherical Laplacian. And then you have lower order terms. And particularly, I showed the general equation for a general scalar of spin weight, but we'll be looking at what's called this psi4, which is this complex linearized Newman-Penrose scalar. So s minus 2 in this equation. And what makes this equation so interesting, and it's really not obvious, is that you can completely reconstruct the dynamical part of the space-time, the part that's the physical but changing part, g mu nu, completely in terms of the scalar quantity. So you can think of it heuristically as the real and imaginary part of psi4 are like the cross and plus polarizations of your gravitational wave. So I'll be talking about the Tucholsky equation today, not the full tensorial Einstein equations. And the Q and M's are then the mode solutions to this equation. So we decompose first in time, and the space-time is also azimuthally symmetric, so we can decompose in modes phi. And then we have the R and the angular piece. And another non-obvious fact, but it's just true, is that the Tucholsky equation separates under this decomposition. So you just get a radial equation. That should be 2 time derivatives here. A radial equation for the radial piece and an angular equation for the angular piece. Lambda is just this separation constant. A, B, C are just constants, some of which depend on omega and m. And the Q and M's are solutions to these separated equations that also satisfy the outgoing wave boundary conditions. So that waves are falling into the black hole, which makes sense. Horizons, things should be falling in. And then at infinity, waves should be going outwards. They should be just propagating outwards. Those are the Q and M solutions. That's the classical picture of Q and M's. So that's the basic review of black hole perturbation theory. I'm going to talk a little bit more about boundary conditions, because it turns out understanding boundary conditions will make you appreciate hyperboloidal coordinates a little more coming up. So let's first just look at Schwarzschild black holes, forget about spin, set A to 0. And we're going to go to the torus coordinate, which we write here. So the black hole horizon is at r equals minus infinity, r star equals minus infinity, and infinity is r star equals plus infinity. Near the black hole horizon, so this is the classical picture in terms of, say, Schwarzschild coordinates. We say, well, as r minus goes to minus infinity, at the black hole horizon, the waves have to be ingoing, which means psi4 has to take the following solution form. It has to have the omega, but then the r dependence has to cancel with the t dependence. So as t is increasing, r is decreasing, the wave fronts are moving into the black hole. So you impose this ingoing wave boundary condition. At infinity, we say it has to be an outgoing wave. It also has to be suitably normalized, so it's like a 1 over r wave, and it has to be this outgoing wave boundary condition. And again, so these are the boundary conditions that, with those separated equations I showed earlier, this is what determines the Q and M solutions. You find the omegas, the r's, the s's, and the separation constant for which all these things are true, and you get this infinite discrete family of omegas. Okay, and I might say later on quasinormal eigenfunction, which is the solution psi4 or Q and E, and then I'll talk about the quasinormal mode, which is omega Q and M. So that I might use Q and E, Q and M at some point, and that's what I'm referring to, the solution and the omega. Just to dig a little bit more, so these omegas, it's an infinite family, and there's different ways you can sort of index these, but I'll index it this way. This is how we did it in the paper. We have P, which stands for prograde versus retrograde, L, which is the L angular quantum number, M, which is that azimuthal number you already saw, and N is called the overtone number. You can visualize it as follows. Here's an example of the Q and M's for a Schwarzschild black hole. The real part's the x-axis, the imaginary part is the y-axis. I should say these are complex numbers, outgoing wave boundary conditions. They're not normal modes. They're going to have a complex part. So let's take a particular angular number L. And we see that even if you fix L, and also this is also for fixed M, we see that we have an infinite family of modes shown by these dots. The overtones index how far along the imaginary axis you are. So as you go up on the imaginary axis, you're going to higher and higher n. And we see that for a given n, there's two modes, like one that's has a real positive imaginary real part, and one has a negative real part. And those are the prograde retrograde modes. So prograde modes, you can think of them and visualize them as modes that are going counterclockwise. Prograde means you're going clockwise around the black hole. Retrograde means you're going counterclockwise around the black hole. So, and sometimes we'll say that P plus is prograde and minus is retrograde. That's the indexing of these modes that we'll use later. Okay, infinite family. This is for Schwarzschild. Okay, now I'm going to talk about hyperboloidal methods, which I think were first discussed in the context of QNMs by Anils and Glenoglu, and then I'll talk about something I wrote to sort of extend it to Kerr, and then a code that sort of used these ideas. So let's go back to this picture of the QNMs. Okay, and I have an amplitude here as well. You can add that. So what's the funny thing about QNMs and like say Boyer-Lindquist or Schwarzschild coordinates? So these modes have to be decaying, so the imaginary part has to be less than 0, right? If you were to expand this thing out, it has to be a decaying mode to be physical. And it turns out the boundary conditions give you that as well. But let's just look at a fixed time slice, t equals constant. Okay, we fix time, and now we just vary r. Let's go out to infinity as r goes to infinity. Well, since the imaginary part of omega is less than 0, we see that as r goes to infinity, these modes are blowing up. As you fix t, you go out in r, now they're exponentially blowing up. That doesn't seem physical. Very strange, but just a fact about the solutions. It's a consequence of the outgoing wave boundary condition. Is this a problem? Is that saying something unphysical about the modes? No. The modes are physical, or they have some physical, you can have some physical understanding of them. This blow up is not a huge problem. Why is that? Because there's no real physics. This is how I think of it. There's no real physics at t equals constant, r equals infinity. This is because if you fix time and you go arbitrarily far in r, you're causally disconnected from the rest of the space-time. No causal observer can communicate with spatial infinity, r to infinity at t equals constant. And these are wave solutions. So they're never actually going to, quote, reach there. In particular, this blow-up you're looking at is an artifact of looking at a damped wave solution over your entire space-time, including at r equals infinity, which is not really where you wanted to describe anyways. So how would you fix this then? How would you get rid of this annoying property of QNMs? Well, let's go to an outgoing null coordinate, u equals t minus r star. If we write the outgoing boundary condition in this coordinate, it looks a lot friendlier. It's just u a over r. And if you looked at u equals constant surfaces, you see that it's perfectly well behaved. It looks like any other wave that you have learned about in the past. There's a 1 over r piece, and there's this u. So along the constant outgoing wave fronts, the QNMs are perfectly well behaved, which makes sense because these u are describing the sort of the causal wave fronts of the theory. For fixed u as r goes to infinity, you're actually looking at places that are causally connected to the interior of the spacetime. I'll show you some pictures later. What about the ingoing solution? It's a similar story with the ingoing solution. You have this ingoing wave. So this is in the ingoing solution at infinity. So as r goes to infinity, what about the ingoing wave solution? That's not physical. What does it look like in this picture? Well, we do these coordinate transformations, and we see that the ingoing wave, which is not physical, it's regular. It's finite, but it's actually oscillating an infinite number of times. So the outgoing wave solution at infinity is this regular, nice looking function, while the ingoing wave solution at infinity, which you want to ignore, is like this infinitely oscillating. In fact, it's not differentiable at r equals infinity because of this infinite oscillations. Interesting fact. Okay, we'll use that fact later. We can now look at the black hole horizon, which is at r star equals minus infinity. We have this ingoing wave solution. We change into an ingoing null coordinate. Similar story. The ingoing solution now is perfectly regular, and the outgoing solution is also at the horizon is this infinitely oscillating piece. So in these null coordinates, the QNMs are perfectly well behaved, and Cauchy-like slicings, they blow up. That's the fact. Okay. It's related to the causal properties of the waves. Okay. Just one more way of thinking of this before we move on. We can look at a compactified coordinate, so we can place minus and plus infinity at -1 and +1. X is this dimensionless quantity. And we say, okay, we have to have these outgoing boundary conditions at plus or -1. And then it becomes clear what I mean by non-differentiable. So at x equals plus and -1, the wave solutions that obey the correct boundary conditions are just these polynomial well-behaved functions with this exponential piece. Well, the ones that don't, these are going to be oscillating an infinite number of times before you reach plus or -1. Okay. That's another way of thinking of it. But if there's any questions, please just interrupt me. I can't see the chat, so if you have any questions, just interrupt. Okay. That's the boundary condition discussion. Let's think of this now in a geometrical picture. So let's go to the Penrose diagram for Schwarzschild-Kerr spacetime. I'll just walk through the definitions of all these quantities. This is the causal diagram of Kerr. So H plus is the future horizon of the black hole. You can think of it as the u coordinate going to infinity while t and r are finite, and it's causally connected to the interior. So like say you're an observer here, you send light waves go at 45-degree angles, you can communicate with the black hole horizon by sending some wave pulse in. And once you're here, you fall into the black hole. Future null infinity is also, you can think of as v goes to infinity with u finite. You can also communicate with j plus or scri plus, future null infinity, by sending a wave pulse and sending it out. Also, if you followed a time-like geodesic, you can eventually reach future time-like infinity, which is denoted by I plus. So any sort of time-like geodesic is going to hit I plus in the future. I naught is spatial infinity. That's where like the t equals constant, r goes to infinity. And it's causally disconnected from everything, the entire space-time, except if you lived on h minus or j minus or I minus, future, the past horizon, the past infinity, or past time-like infinity, you can communicate with I0. Or if you're here, you can communicate with J plus, but nowhere else in the space-time can you talk with space-like infinity, which is these R equals infinity, T equals constant slices. Similarly, for what's called the bifurcation sphere, not always discussed as much, but it's this place here in the diagram, which is at R star equals minus infinity, T equals constant. And again, it can only communicate with along these lines here. You can't talk with anyone else in the space-time. So B and I0 are kind of these funny points in your diagram, but you need it to complete the causal picture. Euler-Lindquist coordinates. On a constant time slice in Euler-Lindquist coordinates, you go from the bifurcation sphere B to space-like infinity I naught. So everywhere Euler-Lindquist coordinates are describing a physical piece of your spacetime, except these like singular points here, which are which you need again to complete the coordinate picture, but maybe they're not as convenient for understanding waves. What about hyperboloidal coordinates? I'm going to call these HPHC coordinates, horizon penetrating hyperboloidally compactified coordinates. We're going to describe what these mean. These are coordinates, again, in this causal diagram picture. They go from, I'm sure many people here in this talk recognize this diagram. It's the hyperboloidal seminar series, but they go from H plus, the horizon, on constant time slices, to scribe plus. So these are coordinates very well adapted to describing waves, because they're describing, they span the whole space. They only touch parts of the space-time that are causally connected to the interior, which is where waves talk to. Okay. So on constant time surfaces, they go from here to here. That's what those dash dots say. And the fact is, QNMs are regular in these coordinates for the reasons I already described earlier. Since they're going from H plus to scribe plus, they're sort of interpolating between ingoing null coordinates and outgoing null coordinates in such a way to make the wave equation, the mode wave equation, regular. Okay. So I'll now describe the derivation, or like the one I use that's used in the code, of turning the Tucholsky equation of Euler-Lindquist into a Tucholsky equation in HPHC coordinates. Okay. One second. So here's the Tucholsky equation again, written schematically, acting on psi4. So to go to Boyer-Lindquist, to just go out of Boyer-Lindquist coordinates, first we transform to ingoing Kerr-Shield coordinates. So you take your time and you convert it into this advanced time v. So it turns out actually v in Boyer-Lindquist coordinates, the v we're going to get here actually isn't a null coordinate, but it's horizon penetrating, which is good enough. And then we're going to also sort of untwist the space-time by redefining a new angular coordinate. We'll then rescale psi4 to make it have a nicer, more regular properties at future null infinity by rescaling in the following way. And then the interesting part is you define this hyperboloidal time variable tau, which we define in the following way. So there's this so-called height function here, and it's rescaling here. So we see that the time as r goes to infinity, d tau equals dt minus dr looks more and more like the u coordinate that I described earlier. So it looks like u as r goes to infinity, it turns into a null coordinate, but everywhere away from infinity, it's a time-like variable still. It's not a null variable, it's time-like. So you can still think of it as like a sort of a Cauchy time hypersurface. Okay, and then finally you radially compactify. So you can put everything on a finite grid. So just choose this simple compactification because it was easy to code. So it turns out the Tucholsky equation under the same decomposition now, it also separates just like in Boyer-Lindquist. So that's great. We still have our separation constants. We still have our equations for R and S. And you can still think of Q and M's are the solutions to these set of equations, for which you have regular solutions now. So you find the omega and the R and the S for which you have a regular solution here. Why is it regular? It's because the irregular solutions are the ones that don't have the right boundary conditions. So I was emphasizing this earlier. So the correct boundary conditions, the solutions will be smooth and differentiable everywhere. While the solutions that have the incorrect boundary conditions, those will not be differentiable at your boundaries. So the solution technique can just be looking for regular solutions. That's the boundary condition you impose. And again, omega is the Q and M, and psi is your Q and E. And it's regular everywhere on your constant tau hypersurface. It's very convenient for numerics because now nothing's blowing up. So there's a code that implements this procedure, and I'll just outline the basic idea of the algorithm here, although I'll spare you too many details. So again, we want to find the omega RS that satisfy the simultaneous system. You can think of this as an eigenvalue problem for your separation constant. So like, what's the omega and the R and the S that will give me the same eigenvalue? The ones that do are the Q and E's. In particular, we discretize the angular equation with using a well-known spectral discretization in terms of spin-weighted spherical harmonics. And we also discretize R using a spectral method as well. And for those who are familiar with pseudospectral methods, what we're doing is something a little bit different that's actually much better well-conditioned. And if you have questions, I can maybe talk more at the end or offline about why the particular method we use here is so much nicer than pseudospectral methods. And both of these discretizations we use, they're very convenient because they automatically, quote, impose correct boundary conditions, which is that these expansions, this discretization automatically imposes regularity of the solution. So any solution I find will automatically satisfy the boundary conditions that we need. So we don't have to sort of impose boundary conditions artificially. And I should say there's a graduate student who, Hungary, who helped implement, in particular, this radial discretization. So it was a collaborative effort to make this happen. Okay. And now I'm going to show you a few examples output from the code, just to give you a sense of like, what do the Q and E's look like? So here I'm showing you Q and E's at a fixed angular number. So I'm just showing you the radial profiles of the Q and E's. On the x-axis is rho, that compactified coordinate. So rho equals 0 is future null infinity. Rho at some, and then the solutions terminate at the horizon of the black hole. And I'm showing the real and imaginary part for Q and E's for S equals -2, psi 4, the lowest level overtone, n equals 0, L equals 2, M equals 2, and for different black hole spins. So we see that these are smooth solutions, and you can find solutions for any sort of, I took this from the paper, so that here A was actually a dimensionless spin, but so A over N equals 1 is extremal, and you see that these are perfectly regular. Why are they terminating at different places? Well, the black hole horizon, it changes as the spin changes. I decided not to scale it, that so you can just get a sense of what these look like. So they're very perfectly smooth, regular. They actually look fairly boring functions, but you can find them for different overtones, L's and M's. So that's example code output. The code will give you, say, the psi 4 and the spectral coefficients as well, if you wish. Okay, example solutions. And I should say we were able to find solutions for much higher spins too. We can go to A equals, I think, 4 or 5 nines, 4 or 5 nines after this, and still find solutions. And with the spectral methods we're using, it turns out it's well conditioned enough that you can do that. We have not looked at extremal. Extremal is a bit trickier. Okay. Of course, more input is welcome. So, I'm describing a code. It's here. It's not perfect. I mean, of course, you could improve the algorithms, make it more stable, look at extremal. So if you're interested, please, reach out. And people have contributed already. So that's the advertisement for that code. Okay. So now I'm going to describe an application of that code to looking at the ringdown and modeling that within linear perturbation theory. So what's interesting about HPHC from a numerical perspective, that now for the first time we can actually impose exact QNM initial data. You can imagine if your code's using if the QNMs are blowing up in your coordinates, you can't just impose them in your computer code, it's going to blow up. So what's nice about HPHC is you can just put in these regular functions and study it. And now, so with this set of tools, you can ask, well, how well in principle, so just linear perturbation theory about a curved black hole background, how well in principle can you measure the QNM content of an arbitrary ring down signal? So forget about real data, forget about full NR. We're going to look at a very clean situation and ask, when can we extract QNMs? When do we confuse them for something else? Sort of starting from the simplest thing you can think of and then build up from there. So I'll be talking about this paper in particular, which Hungary led. And then, so Alejandro is also a postdoc, and Franz is also, you probably know Franz Pretorius. So this, I'll mostly be talking about some ideas from this paper for which we apply these HPHC methods. Okay. So challenges in QNM extraction. So the title already gives you a hint. It turns out even in this very simplified setting, it can still be challenging to measure QNMs in an unambiguous way. That's the punchline. So again, let's go back to the problem. So we're trying to understand ring down, and we're trying to model ring down with QNMs, but we know QNMs they're not like normal modes. They're not complete. You can't describe any arbitrary function, the infinite series of QNMs. Even though there's an infinite number of QNMs, you can't describe any single you want with them. In particular, even within the linearized equation, the Tucholsky equation, there are non-mode solutions. So they're not, you might be able to model them with modes, but they're actually not modes. Of course, there are nonlinearities to the Einstein equations, which might also introduce features to your solution that don't look like QNMs, and you shouldn't model them with QNMs either. Okay. So could these non-mode contributions, can they bias your measurement? Could you be trying to fit modes to something that's not a mode, and then you're sort of incorrectly asserting that you've measured something that wasn't there? Okay, that's sort of like the nightmare scenario people think about in the ring down literature. So I'm just going to flash you some papers. These are all great people, and they're all doing good things. I'm just showing you some of the controversy. So first, there was this paper back in 2019 where they said, okay, we'll take this black hole spectroscopy program. We'll look at the binary black hole merger GW 150914, the first one they saw, very loud event. So they took that signal and they fit two modes. They found that there were two modes present in the ring down signal. The L equals M equals 2, N equals 0 overtone, and then the L equal M equal 2, N equal 1 overtone. So they measured two modes. If you measure two modes, you have two independent measurements of the mass and spin. If they're consistent, you say you found a Kerr black hole. And if it's Kerr, it means it has no hair. So that's what this means. They're testing the no hair theorem because they found two independent measurements of the mass and spin, and they found a result that was consistent with a Kerr black hole remnant. That's what they said. Okay. So first application of this spectroscopy program, to real data, or, one of the first. A different group looked at the data and they said, actually, we couldn't find the overtone. It seemed to be, they found no evidence for the overtone. So the same data set, different methods, overtone versus no overtone. And then there's a little bit of back and forth where people are arguing. But what I'm trying to emphasize here for you is that, people doing different methods can get different answers, at least at first. There already seems to be some motivation to looking at a simpler situation where there's no noise, right? You could argue, well, is the overtone noise? Is it not noise? Are they measuring? Are they not? We'll just go back to like a very clean example and say, well, okay, let's just look at the simplified setting without instrumental noise and ask, okay, can we measure overtones or not? So this was part of the motivation, this back and forth for looking at this sort of simplified setting. So yeah, what can we measure in an idealized numerical setting? We're going to use these HPHC QNM initial data. So I mentioned the QNM code already. We're going to use that to generate initial data for our linearized Tucholsky solver. We're going to evolve the Tucholsky equation in time. So we're going to have a time domain code as well that will also use HPHC coordinates, the same ones that the QNM code's using. So in particular, the background's going to be fixed. Mass, spin, don't change. We can think of this like a numerical laboratory. Pure QNM initial data, we'll also look at non-QNM initial data. We'll ask for these two different sets of initial data, how well can you measure the ring down? Like what modes are you fitting in the signal? You expect in the pure case, you should just recover what you put in. In this case, you might be measuring non-mode pieces. Okay, so this is numerical experiments we're going to be running with HPHC coordinates. First, to give you a brief description of the time evolution code, I guess I should say all these codes are written in this Julia programming language, which is a convenient, easy to use language. So we're solving the Tucholsky equation in the time domain. We're going to decompose in terms of I and phi. So for a given M mode, it's just a 2+1 evolution. You have the angular theta and the radial r and the evolving time. So the 2+1 evolution code. We'll again use this spectral decomposition in the angular direction, and then we'll use finite differences in the radial, which turns out to be more convenient, especially for near extremal spacetimes than using pseudospectral. And we'll also use this fourth order Runge code. So again, if you want more details, please ask, or you can look at the code online. And I should say, Hungry again, we've been collaborating. He interfaced the code with the QNM codes that we can use pure QNM initial data, or arbitrary superpositions of QNM initial data. So we'll actually be looking at arbitrary superpositions as well. Okay, so just to review the basic picture of how people have traditionally fit for QNMs, you take your wave signal, like it looks like this, and you look at some either fixed radial value, or really you extrapolate to functional infinity, and you look at your time signal, and you want to fit the modes there. So it's like a 1D kind of signal, and you want to fit the best fit amplitudes. So A are these complex amplitude numbers. So they include amplitude and phase information, and you're fitting modes with this 1D signal. And for example, you might want to minimize the least squares. You might take your signal S and subtract it and want to minimize that. That could be one way you do this. This method, you're not looking at any other information beyond, say, angular and time. So I should say this is also like you do an angular decomposition too. So you might look at like the L=2 spherical harmonic times signal and do this decomposition. But you're not looking at the radial information. So in particular, from a numerical, LIGO isn't going to tell you the radial information, but from a numerical relativity perspective, you do have radial information, and that could be giving you valuable signal to noise in your fit. That could make your fit less, give you more information in your fit, higher signal to noise. In particular, you could imagine, in principle, a solution that looks like a QNM at a fixed radius, or the extrapolated waveform looks like a QNM. But if you had access to the radial information, you would see actually it's a QNM it's something else that's masquerading as a QNM over some finite time interval. or some superposition of, it looks like a superposition of Q and M's, but it's actually something else instead. So if you looked at the radial information, it might tell you, it might actually help break degeneracies in your fit. And HC coordinates, it's very straightforward to include radial information because the modes, again, are regular there. So you can just do your fit not just at one fixed radius, not just at future null infinity, but at many radii. Gives you more signal to noise. Especially for a linearized code, you can just fit over the whole domain. Okay, so straightforward way to incorporate radial information. So I'll describe how that works in the fits that we looked at for the experiments we ran. So I'll define the mode to just call it phi. So I don't have to keep writing things over. This is like a QNM, capital phi, for a particular prograde L. And I'm not going to include M because we're already assumed that we've decomposed in M quantum numbers. So we factor out the e to the ion phi. So we have our mode frequency here and our radial piece and our angular piece. And here I have these I, J, K, because now just imagine we've discretized the space-time, sort of schematic, but I, J, K are integers, and now we've discretized our space-time and time, radius, and angular directions. S is this a particular solution to the angular equation, this spheroidal harmonic. So now we want to do our fit. So we take a time and we want to fit psi and its time derivative as a sum of modes. So you have the amplitudes, these are the modes. And we choose psi and its derivative because that's a complete set of Cauchy data for a given time. So if I have psi and psi dot, I can evolve in time. So we'll fit for these simultaneously. So you can rewrite this as a matrix equation as follows, for where J is indexing your mode quantum numbers and I is indexing your time space indices. So you can rewrite it as like a matrix equation for your amplitudes. And then from that perspective, from this particular way of thinking of data analysis, finding the amplitudes is just inverting a matrix, quote, just inverting a matrix. So, and this matrix equation here, you can, so now that you have this matrix equation here, you can think of two different things you could do. You can either fix J and K, you can fix your radius and angular information. This is a bit schematic, but I didn't want to have too many indices. You fix your radial and angular information, and then you fit only in time. So you could invert this matrix, sort of fixing these numbers, and you have a smaller submatrix now, and you're doing a time fit. Or you can fix your time, because now that you have radius and angular, you can actually just do a complete QNM fit at fixed time intervals, just TI, and again, do the matrix inversion. Or you can do the matrix inversion over all I, J, and K, and then you're fitting radial, angular, and time, everything together over some interval. So from this perspective, it's sort of just a way to package it all. You can do either fixed time fits, fixed radius fits, or do the whole thing. And you can compare what you're going to get from each of these kinds of fits. You should think of this as, this is least squares. This is a least squares fit. So you can think of this as minimizing some quadratic residual where psi is your solution, and then you want to minimize this. You want to minimize the residual, quadratic residual, where these are sums over QNMs. And I forgot the amplitude. There should be an A here too, but okay. So this is, you can think of it as a least squares. Okay, again, this is not like a foolproof method. The QNMs aren't complete. So we're just going to we're trying to minimize the residual over QNMs. We're going to be trying to fit non-QNM pieces too that might be present in the solution using this fit. So yeah, we will try to minimize the residual no matter what happens. I should also say in the code, the actual fit, so Hongre's here, the actual thing he did is a little bit different from what I described here, but this was a simpler way of describing it. So I'm just describing this here because, and morally speaking, this is what we did. We did this sort of least square fit over these indices. He did something a bit more convenient for numerics, which we can talk about more later, and it's described in the paper. Okay. So now that we have our fitting procedure, we can ask, well, what does it mean to fit a QNM? So when have we actually found a QNM? So I'm going to use a notion of stability that I think was introduced in this first paper here, and I forgot to be this paper here. And if it was introduced earlier, someone should tell me, but this is where I first learned of how to do this. So you take your fit for a mode AJ, and you then rescale out the decay. So you multiply it by the mode that it corresponds to, and you take the decay out. So if this was or you can do over some fixed time interval and you multiply by the decay. So if this was an actual QNM, this quantity here shouldn't change with time because it's decaying. Your fit for A is going to be decaying just as fast as this sort of, you're fixing to it. So if you found a mode, this quantity shouldn't change with time. The mode fit is quote stable. So constant, this quantity here, you've quote measured a QNM. And if AJ is varying with time, if this quantity here changes with time, you could say, okay, you actually haven't found a QNM because it's decaying too slowly or too quickly to actually be quote a real QNM. So when you say a mode's stable, it's sort of you visually inspect this quantity here and ask, is it constant? That's what people, many people are doing this right now. That's how they kind of think of it. All right, so that's what I mean by stability. So I'll be showing plots of this quantity here, and you can see, okay, is it changing or not? So yeah, first numerical experiment, pure QNM initial data. So we'll just take some linear sum of QNMs and we'll put it in our initial data, will evolve in time. Can we recover the QNMs that we put in and nothing more? The answer is yes. So good, first step. And you can do this with the time-only fit. You can also do this with this time and space fit. Both work great. So first, I'm just going to show you psi4 here for different modes. So here, Hong, we put in a n equals 0 overtone. We put in a and two higher overtones, n equals 3 and n equals 4. And then we see that there's n equals 2. He's also trying to fit for 2, n equals 3, and n equals 5. And he sees, you can't find those, which is good. It's like consistent with noise. And then eventually you hit the noise floor and you're consistent with noise. So point is, you put in a few QNMs, you try to fit for other ones, you don't find it with both methods. Great, that's good. So we have like this notion of stability, which you can show here. So we rescale by the decay. So I first showed you something that makes more sense, and then I'll show you the stability sort of plot. So here he's multiplying the amplitudes by their decay, and we see that the n equals 0 overtone, perfect, stable, flat. We're measuring one overtone. These other two overtones we're also measuring great until they hit the noise floor, and then they start changing because like this is flat, and you multiply it by an exponential, and now it starts to change. Similarly, for these other modes, they're changing with time. We don't get a stable fit. And so for the spatial and space-time fit, we both obtain this. So that's stably recovered QNMs, great. So then this the simplest scenario, the cleanest scenario, good, you can measure it. Okay. Now let's try non-mode initial data. We'll just choose some random Gaussian pulse. It has some width W. It has some time derivative to make it ingoing. Okay, try this. This will have, since the Tucholsky equation has non-mode solutions, even though it's a linearized solver, there will be non-mode solutions present in the equations. So in the solution that will be fitting. So what happens to our modes fits? Now the mode fits get a little more complicated. So let's go through this a bit more slowly. So we're going to rescale each mode. These are for different spins. Let's just start with A equals 0. So at initial times, things are messy. We don't see any modes at initial times. This is because the solution is contaminated with what I called prompt solution, the prompt response to the Tucholsky equation. There's like this initial transient piece that's not modal. It's just reflection of the particularities of your initial data. That's what we're fitting here. We see the amplitudes are varying. But then we get into this intermediate period. And we see that there's intermediate period, our fit. So here dot means time only fit. Solid lines are space, the spatial only fit. So we fix time, like they're the exact opposite of each other. Time only fit, we're only fitting with time information at a fixed radius at future null infinity. And spatial fit, we're doing fits at constant fixed time slices over the entire radial information. So we see that the first overtone, very clean, we get the first overtone. It's very stable for both fits. The red is this is a 0th overtone, I guess, is blue. The first overtone is red. We can fit that stably, but eventually we start seeing non-mode things going on here for both fits. Similarly, and then for higher overtones, we don't really seem to get any sort of quote notion of a stable fit. In case you're wondering what T1, T2 is, T1 is when we measure the maximum amplitude of the waveform at the horizon, and T2 is when you measure the maximal waveform amplitude at future null infinity. It's just a sort of a marker of like when is the waveform sort of passed out of your domain, the transient. So okay, so we see we have trouble measuring higher overtones even in this A equals 0. Again, for spin 0.7, which is more closer to like the remnant black hole equal nice binary, we get the first and the two overtones, 0, 1 pretty well. Higher overtones, I mean, you can squint at it and say maybe we've seen 2 and 3, but it's not really clear and they're jumping all over the place. And finally, for very close to extremal, we see that we can get n equals 0, but nothing else. Interesting. Okay, so as you go to closer to extremal, it seems like we're having a harder time fitting even in this very, very simplified setting. Okay. Let's take a closer look at the time-only fit. So the time-only fit appears, I mean, you could claim if you wanted that they look slightly less stable. So for example, here, the red solid line seems to be flat, while the red dot line is starting to go all over the place at a much earlier time, right? This is around 30 m, and we're staying flat till around 60, 65 m. And remember, these are exponentially decaying functions. So like this is a huge amount of time that you have extra in your fit from the space, if you include the spatial information. Okay, similar here. So you could claim that if you wanted. We don't seem to be getting a consistent fit except for like the first two modes. But now you want to evaluate the time-only fit. What's another measure of the time-only fit besides looking at this stability diagram? So what we did, or what Henry did, is he did the time-only fit at several different radii, including future null infinity. So he has like this family of amplitudes for different radii. And then, so if he was actually measuring a mode, so this is something maybe more akin to what you might want to do with a full 3+1 code. You fit the amplitudes at different radii. So if you had a mode, the amplitude should look like this. So this would be an I here. It should look like a constant prefactor times the radial profile for the mode. So to judge how close this fits are to this, he computes what's the mismatch between the A and this rescaled. So he takes his A's at different R's. He takes this inner product, he just integrates them against each other. He integrates A against the radial profile for the mode he wants to fit, and he divides it out so that the proportionality factor cancels out. So if the mismatch is 0, A is obeying just as you would expect for the radial profile for a mode. If A is 1, if N is 1, then it doesn't look at all like a mode. So this is what he did for the same experiments I already showed. So blue is the 0 overtone and equals the first overtone. We see that, and he sort of arbitrarily said if the mismatch is less than 10 minus 3, it's like, okay, success. The time only fit is seeing the overtone. I should say these are all L equal to M equal to mode, different overtones. So we see that the R and blue, they dip below the gray briefly, which seems to indicate you're measuring a mode. Although you could also argue that, in fact, you want not just the mismatch to dip below to be small, you would actually prefer the mismatch to stay constant in time too, because it means like the radial profile isn't changing in time. If the mismatch keeps jumping around, it's telling you that your radial profile is sort of changing throughout time. It's close, it looks close to a mode, but it's also, its functional form is changing, which could, if you were really strict with yourself, you could say, this red isn't really indicating an overtone fit because the mismatch is varying in time. Well, the blue, it's staying constant at some point. So it's a real, quote, real measurement. But it depends on how strict you want to be with yourself. So again, A of 7, you could claim, okay, either it's 2 overtones or it's 0 overtones. And we see for the extremal case that either you're measuring at most 1 overtone, maybe 0, because it's changing in time. You could say, well, actually, no, this is maybe this slow varying in time is actually due to like some other sort of non-mode solution, like a tail or something. So if you want to be really strict with yourself, you could claim, okay, the time only fit measures nothing here, but depends on your perspective. Okay. Yes, that's one test we did. Okay, so the conclusions from these experiments, we have this idealized scenario, linearized evolution about occur. Pure QNM initial data, fine, everything works. If we don't use pure QNM, things get more complicated. We measure 1 to 2 modes. With the experiments that we did, using the methods that we did, there might be other methods you could use that get different answers. We're not sure. This is just what we did. Including radial information, you could claim helps stabilize your fit. You seem to extract modes more easily if you include that radial information, which maybe makes sense because your SNR is now higher. You have more information you're playing with. Oops. Briefly, how would you extend this to, codes that do real 3+1 simulations? You don't want to measure over the entire space-time because definitely near the black holes, things are very nonlinear. So it's definitely not going to be modal near the black hole horizon. But you could imagine instead doing it, these sort of looking at radial information in the radiation zone, where the gravitational fields are weak, and you expect it to look more mode-like. In particular, if you're looking at Cauchy characteristic extraction, for example, so you have a time-like slicing, like this, the spectral code and other codes are kind of doing this now. You have your time-like slice, and then you match to some null slicing. You can imagine, okay, well, out here in this linearized null coordinates, first of all, it's null, so the QNMs are going to be well behaved here. Just don't use J+, use like J++ a little tiny bit away from it. Maybe a little bit of radial information. Does that help your fit? I won't claim it will because no one's done it yet, but it's definitely an intriguing thing to look at, I think, at some point. So that's one potential extension to full NR, is to look at these CCE codes and just look in this region. Yes, so to conclude, that was our numerical experiments. I hope I convinced you that HPHC coordinates are interesting and they have a lot of interesting applications. I described one application to ringdown and looking at QNMs. And if anyone has any questions, please feel free to ask. Thank you.